Welcome to Day 4 Exponential Equations. You will need the 3 P's, can you remember what they are, as well as a graphing calculator. Last time, we figured out how to manipulate and solve equations that had a variable in the base and a fractional exponent. But what happens if the variable we are looking for is part of the exponent of our equation? The answer once again relies on a keystone idea, and that is having the same base on both sides of the equation. To do this, I'd like to introduce the idea of the lowest common base, or the LCB. We can think of the LCB in terms of two details. First, the base is the lowest factor of the number written to a power. To find this, we can use an idea from 8th grade known as the factor tree. Second, the base will always be a whole number greater than 0. That's not to say that the exponent cannot be negative, but the base itself will always be a positive number. The idea becomes a little bit more clear in our first two examples. If I rewrite 9 as a product of its LCB, I can easily see that 3 is the lowest base, and it is raised to the second power, so I can rewrite 9 as 3 to the second power. Similarly, in example 2, I can break up 64 into 8 times 8. And I could say, well, this is 8 to the second power, but that would not be in terms of the LCB. To rewrite it in terms of the LCB, I need to go a little bit further, splitting the 8's into 2 times 4, and then going even further and splitting the 4 into 2 times 2. What I can see now is that 64 can be rewritten in terms of one base, 2 to the 6th power. And now I am done. In examples 3 and 4, I have a fraction. Now I know what you're thinking. How do I factorize a fraction? Oh my goodness! Remember that we can rewrite fractions with no denominators by negating the power of the term in the denominator. In example 3, we can easily see that 1/5 can be rewritten as 5 to the negative 1 power, and we're done, because 5 is its own LCB. In example 4, we can start by taking 1/16 and changing it to 16 to the negative 1 power. But 16 itself can be factorized, so let's consider its factor tree. By splitting it up into its prime factors, we see that 16 becomes equal to 2 to the 4th power. So we substitute this back into our parentheses, like so. And notice that we still have that negative 1 on the outside. So by distributing, I can see that 1/16 becomes equal to 2 to the negative 4th power. And now I'm done. Now that we know the keystone concept, we can look at the process to solve exponential equations. In other words, equations where the variable is contained within the exponent part of the expressions. To solve, first we must have like bases on both sides of the equation. This might require rewriting one or both sides of the equation, as we did in the previous examples, so that both sides have the same base. Second, once you have a common base on both sides, you can drop that base and set their exponent parts equal to each other. And we'll see how to do this a little bit more in our examples. Finally, solve for the variables using algebraic manipulation, and then check your answer by placing your solution for the variable back into the original equation and seeing if it holds true. Now let's look at a couple of examples to practice this process. In example 5, we should notice that we have two sides with different bases, but both with exponents that have the variable x. To begin solving, we must first have the same base on both sides. So, I will first place parentheses around the bases, like so, and compare them. Since 3 on the left cannot be broken down further, we will factor 27 and see if we can find an equivalent expression that has 3 as its base. Using a factor tree, we can see that 27 can be rewritten as 3 to the 3rd power. I can now rewrite my equation with 3 to the third replacing 27 within the parentheses. Note that I now have a power law situation on the right side. So I multiply the exponents together so that I have 3 to the power of 3x plus 3 on the right, and on the left side I have the same 3 to the 2x power on the left. Now you can see that I have both sides of the equation with the same base, and I can proceed to step 2. Once I have common bases, I can drop the bases and set the exponent parts of both sides of the equation equal to each other. So here, I'm going to drop the 3's from both sides, like so, and set the exponent parts equal to each other. On the left, I'll have 2x, and on the right, it will be equal to 3x plus 3. Now we simply solve for x using algebra. I'm going to move 2x from the left to the right, and I'm going to subtract 3 from both sides. I should be left with the statement negative 3 equal to x. Now I'm going to check my solution by plugging in that value of negative 3 for x in the original statement, or rather the original equation, 3 to the 2x equal to 27 to the x plus 1. Note that I'm substituting in negative 3 for x. And I ask myself, does the left side, once I plug in this value for x, equal the right side once I've plugged in this value for x? What I should come out to is 1 over 729 equal to 1 over 729. So my answer checks out, and I know that I have the correct solution. In example 6, both sides will need to be rewritten in terms of a common base. I start by remembering that the left side, which is 1/9, can be rewritten as 9 to the negative 1. I then use the power law to distribute on both sides so that I get a statement 9 to the negative x is equal to 27 to the 1 minus x. Now I proceed with my steps. My first step is to have both sides of the equation have the same base. Usually I would use a factor tree, but since I've used both of these numbers in previous examples, I know that 9 can be rewritten as 3 to the second power, and 27 can be rewritten as 3 to the third power. So I'm going to use these values and substitute them back into the equations like so. Note that I'm using parentheses to represent the numbers themselves. Now once again, you can use the power law to distribute. Make sure on the right side that you're distributing to both terms that are outside of the parentheses, and you should come out to a statement on the left 3 to the negative 2x, and on the right 3 to the 3 minus 3x. Note that both sides of the equation now have the same base and different exponents that involve the variable x. So since I have both sides with the same base, I can drop the base and set the exponent parts equal to each other. In other words, I compare the exponents. So I'm dropping my bases, and I will set the exponent parts equal to each other, giving me the statement negative 2x equal to 3 minus 3x. Now I solve using algebra. I'm going to add 2x to both sides, or rather add 3x to both sides, and I should come out to the statement x equal to 3. Once again, I'm going to check my answer by plugging my solution for x, 3, into the original equation for my values of x. Note here that I'm rewriting the original statement using 3 in place of x. Now remember that the point of the check is to see if the left side of the statement equals the right side of the statement after you've plugged in the value. What you should end up coming out with is 1 over 9 to the third equal to 1 over 27 to the second, and contrary to what is posted here, you should have 1 over 729 equal to 107.29, and it checks out. Here are the things that you should be able to do. If you're having trouble with any of these skills, go back and rewatch the video focusing on the skills that you're struggling with. Until next time, this is Mr. Mackman, signing off.